All right, what we're going to do now is we're going to look at the mean value theorem and basically practice knowing when we can apply it and when we can't. So for each of the following functions described below, so there's just descriptions of certain functions, determine whether or not we can apply the mean value theorem on the interval -3 to 3. If it can be applied, we have to talk about why we know. If it cannot be applied, we'll talk about why not. So the example is that a function is differentiable for all real numbers, and your mean value theorem can 100% be applied in this scenario. Since the function is differentiable, that differentiability implies continuity, because if you have a function that's discontinuous, it's automatically you can't take the derivative of it. So if we know that our function is differentiable, it has to be continuous. So it's certainly continuous on the hard interval, -3 to 3, right? Remember, this includes -3 and 3 in its answers. And it's differentiable for all real numbers, so it would certainly be differentiable on the open interval, -3 to 3. Okay? All right, so let's see if this is enough to use the mean value theorem. F of x is continuous for all real numbers. Nope. The MVT cannot be applied. And that's because we don't know anything about its differentiability. Whoops, appled. So we know for sure it's continuous from -3 to 3 because it's continuous for all real numbers, but I have no information whatsoever about whether or not I can take the derivative from -3 to 3. So there's just not enough information to be able to use the MVT. Okay. F of x is differentiable on -3 to 3. So that satisfies the derivative part, right? Checked, the function is differentiable from -3 to 3. And that actually implies continuity from -3 to 3. The problem lies, boop, boop, with the fact that I have no idea what actually happens at 3. So knowing that my function is differentiable only works from -3, whoops, to 3, and so that's the only part that works for continuity as well. You can only say that my function is continuous on the exact same interval. I can't know anything about what's happening actually at -3 and 3, and I need my function to be continuous on the hard interval from -3 to 3 in order to use the mean value theorem. I need little inclusive pieces here, which I currently don't have, and so we can't use the MVT. All right, so here I have a function which it looks a little bit funny written this way, so I'm actually going to rewrite it before I take a look at it. So this is the function, this is the cube root of x squared. And then I'm basically just trying to figure out, is there anything that I could plug in here that would make my function discontinuous? So I can have 0 underneath the cube root, I can have positive numbers, and I can have negative numbers under a cube root. So I would say that this function is for sure continuous from -3 to 3 because I think it's continuous for all values, all real numbers. But the one thing I want to check now is it differentiable on that interval? So if I take the derivative, which actually is easier using this first part, but if I take the derivative, I get, so let's see, 2/3 x to the -1/3, which is, bring down the 2/3, multiply 1 from the power. If I rewrite it though, that gives me 2/3 cube root of x. And so now I ask myself the same question. Is there anything that would make this undefined or a negative under the square root or anything like that? So first of all, I can have positive and negative numbers under a cube root, and you can have 0 under a cube root. The problem comes with the fact that the cube root is in my denominator. If I plug 0 into this function, I'm going to get 2/0, which is undefined. And 0 is definitely in the interval from -3 to 3. So I would say absolutely not. This function is not differentiable on the open interval -3 to 3. Therefore, you cannot use the mean value theorem. And that's why it's so important that we check these things before we just jump into automatically using the mean value theorem. So nope, sorry. All right, our absolute value graph here. If you know what an absolute value graph looks like, we know that it's a continuous function, so it's going to be continuous everywhere because I could plug in negative numbers, I could plug in 0, I could plug in positive numbers, so from -3 to 3, it's definitely continuous. But again, I run into a bit of a differentiability issue when I try to plug in 0. An absolute value graph, if you know what an absolute value graph looks like, it looks like this normally. And then if I do an absolute value of x plus 4, that just moves it, whoops, that just moves it 4 up. The problem comes here. Whenever you have a corner or a cusp on a graph, that means it's automatically not differentiable there. I can't find the slope of the tangent line. And so this would be not differentiable at 0, and 0 is in that interval. Oops, these should be soft brackets, which means that my MVT cannot be applied because I don't meet the requirements to use my mean value theorem. All right, let's talk about this function. So sine of pi x over 3. So I know all sine functions in general look like this, right? And so I would say, oh, that's a cosine function. My goodness, you guys. So I would say that a sine function is definitely continuous for all of its real numbers from -3 to 3, especially. And then I would maybe want to look at what the derivative looks like as well. So f prime of x. I'll have a little bit of chain rule going on here, but your derivative would be pi over 3 cosine of pi over 3x. And we know that a cosine function basically looks like, even if you multiply by pi over 3, that's just going to make it a little bit taller. So it would just be a little bit bigger this way. So that means that a cosine function would be continuous, which would mean that the derivative of this function would in fact work from -3 to 3. So we found our first one where our MVT can be applied. Awesome. All right, let's go ahead and look at tangent. Now, automatically in our brains, we should be set off a little bit because we know, even if you don't know what a graph of a tangent function looks like, which very typically looks like this. And it has these nice asymptotes going on. You also know on your unit circle that at certain points on your unit circle, so here's 0 degrees, which is 1 comma 0, that would be tangent there would equal, whoops, would equal 0. Tangent up here though, 0 comma 1 would be undefined. So tangent of pi over 2 would be undefined. Whoops, I choose gross looking. And so basically you just have to ask yourself, well, is pi over 2 in between -3 and 3? Is my function continuous from -3 to 3? And we would say definitely not, because pi is about 3.1 divided by 2 is about 1.5-ish, and that falls in this interval, and so my tangent is undefined there. So automatically you can plug in no matter what your x value you plug in there, you would end up getting some value where your tangent would be undefined between -3 and 3, which means it's not continuous, so it's not differentiable, which means the MVT cannot be applied. All right, and then it looks like our last one. So for this guy, we have the function at 1. So the only thing I'm going to look out for, because I know an x squared plus 3 graph, that's a parabola, that would be continuous everywhere, and so would a linear function. We just have to see if at its breaking point it would be continuous. So let's check it first. So we're checking for continuity at -3 comma 3. So let's do our check for continuity. So we'll find f of 1 first and foremost, which would be the top function. So f of 1 would equal 1 squared plus 3, which is 4. That's also the left-hand limit of my function. And then we'll check our right-hand limit. by plugging into the bottom function. 2 times 1 plus 2 is also 4. Okay, so I would say it's continuous because, like I said, I know my parabola is continuous everywhere, and linear function is continuous everywhere. We just had to check our breaking point to see if they would match up, essentially. And they do, so we'd say it's continuous. Now we're going to check the differentiability. So I'm going to find f prime of x, and I'll get 2x, and I'll get 2. And so then we basically have to check the same thing and see if it's continuous and differentiable. I know this is continuous everywhere because it's a linear function. This would be continuous everywhere because it's a constant, but I have to check and see if at 1 they would match up. So I'm going to find f prime of 1, which is 2. That's also my left-hand limit. And then my right-hand limit would also be 2. And so, yes, I would say this is differentiable from -3 to 3. Therefore, the MBT can be